So far in calculus, we've been focusing on what I call explicit functions. Functions where you have a y and it's just given as some function of x. And then the standard problem that we might ask is, can we take the derivative of this function? We'd ask for what is f prime of x. But a lot of functions aren't actually given explicitly, they're given instead implicitly. So here's an example. I have some equation, x squared plus y squared is equal to 1. Now, for every value of x, there may or may not be some number of y's that you can find such that for that x and y pairing, this equation is true. So we want to try to see if, given an implicit function, some just equation involving x and y, and perhaps more variables if they were around, can we tease out explicit functions from them? For example, this equation is known to be the equation of a circle. So I can graph it and it's going to look like this. Indeed, this is a circle of radius 1, and all of the different points that are going to be on this have that x squared plus y squared is equal to 1. Now, let me try to solve and make this y as some function of x. Let's see if we're able to do that. I'm going to put all the y's to one side first. So I'm going to say that y squared is equal to 1 minus x squared. And then I want to not have y squared, I want it explicitly as y as a function of x. So why don't I take a square root? But as soon as I have square roots, we remember there's an issue because there's positive and minus square roots. So I kind of want to write it like this. Y is plus or minus the square root of 1 minus x squared. Either would be satisfying this original equation. But this violates the vertical line test. To be a function, it needs to be the case that for every x value, there's exactly one y value. Or if I want to think about it graphically, what you do is you draw a vertical line and you say, well, look, for this particular x value, there's two different y values, this top and this bottom, that correspond to it. So it's not the case that we can find one function y equals f of x that describes this entire circle. But you'll notice that I have a yellow semicircle on the top and a red semicircle on the bottom. I could break these out as two different functions, one that describes the top, one that describes the bottom, using the plus and the minus that I have in my square root. In other words, what I have is two different functions. One, the y equals the positive square root that describes the top, one, the negative square root that describes the bottom. And so that this one equation has resulted in these two different explicit formulas. So maybe now my question should be, I want to find the derivative of y with respect to x. And the idea is going to be that if I want to take the derivative over here, I'm going to use the yellow. And if I want to take the derivative down here, I'm going to use the red. Now, we might ask the question, what's the derivative of y with respect to x? One answer would be, I could just look at where I'm interested in. If I'm interested here, I'm going to use the positive square root, the yellow. If I'm interested in the derivative down here, I'll use the negative square root, the red. But I want to have a bit more of a systematic way to compute the derivative. So the way I'm going to deal with this is I'm going to take my x squared plus y squared equal to 1, but instead of a y, I'm going to write y of x, where I'm thinking that y implicitly depends on x, even though I don't necessarily know what the actual function is. It's just some function of x. Then this is an equation, and I could take the derivative with respect to x of both sides of that equation. I can add 1 to both sides of an equation. I can take the derivative of both sides of an equation. So let's see what happens if I do that. So I'm taking the derivative of the x squared, the derivative of the y squared, and the derivative of the 1. Now the derivative of the x squared, that's entirely reasonable. It's just 2x. The derivative of the 1, we know what that is. That's just 0. But what about the derivative of the y squared? What I want to think about when I take the derivative of the y squared is there's an inside function, the y, and there's the outside function, the squaring function. So y squared is a composition. There's an outside and there's an inside. So when I take its derivative, you take the chain rule. Derivative of the outside, so 2y then times the derivative of the inside times y prime. So putting all that together, what I'm going to get is this formula. X squared down to the 2x, y squared down to the by chain rule 2y dy dx, and the derivative of 1 is just going to be 0. Now that I'm at this stop, I can just do a little bit of rearranging and identify the dy dx. It's minus 2x over 2y, or minus x divided by y. Now I want to note that just notationally I've written y of x in all of these different spots. But it's quite conventional for us to not actually write the of x everywhere, and instead just to treat this as y's in every one of these spots. But we're keeping in our mind that indeed these are going to be functions of x. And so that I need to indeed apply the chain rule at these spots. So now let's return to the original problem, but now I'm asking the slope at a particular point, minus 1 over root 2 plus 1 over root 2. And you could take the squares of these things and it would add up to 1. So it is indeed a point on a circle. Indeed, it's a point on a circle right about there. So how do I figure this out? I know that the slope of the tangent line is given by the derivative, is given by dy dx. And our formula for this was minus x divided out by y. And then if I want to evaluate this, these big long vertical lines mean evaluation. If I want to evaluate this at the pair xy equal to minus 1 over root 2, 1 over root 2, well, we could do that computation. And then when I evaluate at this particular point, what I'm going to get to, well, minus minus is a positive, so I'm going to have just the 1 over root 2 on the top. And then plugging in for the y, which I have right here, is the 1 divided by root 2. And this whole thing is just going to be equal to the value of 1. And then if I want to plot it, so I'm looking around here, and this is going to be my tangent line. It looks like I've got a nice slope of 1, and it occurs at this point, minus 1 over root 2, 1 over root 2. Note, by the way, if I asked a slightly different question, what happens at this point right here? This is the point x equal to minus 1 and y equal to 0. Well, if x is equal to minus 1, then I'm going to get a 1 here. Y divided by 0, that gives me a vertical asymptote. So at this particular point right here, we're going to have this straight up vertical line. That is what the slope of the tangent line is. Likewise, we could answer the same question over here. Again, our y is going to be 0. Again, we're going to have a division by 0.